Hello, can everyone hear me? All right, we're going to start the lecture now. Thank you everyone for coming. My name is Erica Hamden. I am a postdoc here at Caltech. I build telescopes and study galaxies. I am replacing Cameron because he is in Oregon scouting out locations to see a solar eclipse next August. But he'll be back next time. So the plan for tonight is Jessie will be giving us a fabulous 30-minute lecture, and then we'll have 90 minutes of stargazing on the fields that are directly behind the building, which is that way. So to get to stargazing, if you haven't done it, you leave through the same doors that you came in, and then you turn right, and then you make another right, and then you make a third right to go onto the field. And you should see telescopes there, so it'll hopefully be obvious. If you don't want to go stargazing, I'm going to give a brief presentation on the Perseid Meteor Shower, which is happening now. And then we'll have a Q&A with some resident Caltech and JPL experts on whatever you have questions on. So the skies are clear, so observing will be on after this. And if you didn't pick up a flyer when you came in, we have just a schedule of the rest of our lectures for the rest of the year. Our next lecture will be on September 9th by grad student Anna Ho, and she's going to be talking about the invisible universe revealed from glowing dust to spinning stellar corpses. Also, we've started doing a program called Astronomy on Tap, which is where astronomers from Caltech and Carnegie and JPL give brief lectures about interesting, fun space topics in a bar setting. So that next one is going to be on August 22nd at Der Wolfskopf, which is in Old Town Pasadena. All right, and also this is sort of an important announcement if you're a regular attendee of these, that for a variety of reasons, the next couple of lectures are not going to be in this room. They're going to be moved to a larger auditorium called Baxter, and we'll have the stargazing somewhere else because the field is getting replaced with turf, so we can't actually go out on it for a little while. But there'll be lots of information on the website, so check back, and we'll hope to have it settled in the next couple of weeks before the lecture in September. All right, so I think that's it for now, and I'm going to turn it over to Jessie, but just to give you a little bit of introduction. So Jessie is a staff scientist at the NASA Exoplanet Science Institute, which is very close by on Caltech's campus. She works on the Kepler Mission, which is a space telescope that she will describe to you in moderate detail in her talk today, which the entire focus of the telescope is to detect and characterize exoplanets, and she has a particular, and the telescope has a particular focus on determining how common Earth-like planets are in our galaxy. So it's a very exciting subject for basically everyone on Earth. All right, so Jessie, take it away.
Thank you so much. You can hear me? All right. Awesome. Okay, so hopefully you don't think of this as a lecture. It's more like a journey of discovery that we're taking together over the last 400 years. And what I'm going to be telling you about is the history of the search for and the discovery of and the characterization of exoplanets. And you're like, whoa, Jessie, wait. Exoplanets? What's an exoplanet? So this is a diagram of our solar system with more lens flare than a J.J. Abrams film. Thank you, JPL. We have one star in the middle of our solar system. It's a pretty boring average G star. We have 8 planets. Boo, hiss. I hear disagreement from the audience already. That's another talk for another time. We have dwarf planets, including infamous Pluto, and 4 other that are official dwarf planets, and then many other which may at some point be given the status of dwarf planet, but at the moment are not. We have minor planets, which includes basically everything in the solar system that's not the star or the planets. It's the dwarf planets, the asteroids, the Trojans, Kuiper Belt objects. Of those, we've catalogued more than 700,000. There's a lot of stuff out there. But exoplanets, what are they? So let's talk about a concept called cosmic pluralism. I have 2 things I have to press buttons on, so we're going to work this out. Cosmic pluralism is this idea that Earth is not the only planet out there like the Earth, that there are other worlds out there far out in the galaxy that look like Earth. Now I'm going to cheat a little bit and go slightly further back than 400 years. I'm going to go all the way back to 600 BC. And this was a time when, you know, if you were a certain type of person in Greece, you could just sit around and talk about ideas all day. And one of the ideas they talked about, in a purely hypothetical sense, nothing to do with actual reality, kind of like the way we talk about multiverses today. It's like a cool idea, but they talked about Earth and whether Earth was the only one of its kind or whether there were many Earths. So two you might have heard of, Plato and Aristotle, argued that Earth was singular, unique, that it was the only one of its kind. And then we kind of stopped talking about it for a while because, as I said, it was kind of a bit hypothetical. We have to fast forward 1,800 years, which is a long time, and we find Fakhr al-Din al-Razi, and I apologize, I'm probably massacring that, who was a Muslim philosopher. And he had this quote in one of his works: "Therefore, he, the Most High, has the power to create 1,000,000 worlds beyond this world, such that each one of these worlds would be bigger and more massive than this world, as well as having the like of what this world has." So this is really fascinating. What he's done in the Quran, there's a title of the God in the Quran, which is the Lord of Worlds, plural. There's an S at the end, the Lord of Worlds. And he takes that and goes, okay, he's, you know, omnipotent, omniscient. He has the power to make all the worlds. That's fine. That's not, you know, in contradiction with anything else that we've read in the Quran. Now remember this, because this is important. So again, now we wait a little while, because this is still purely hypothetical. Then we come to the Renaissance. Now the Renaissance is a cool time. You have art, you have literature, you have music, culture, and science all going through this massive revolution. It's a particularly interesting time for astronomers. You have Hans Lippershey inventing the telescope. You have Galileo pointing it at the sky for the first time. You have Copernicus ruining every toddler's cherished fantasy that they're the center of the universe. And then you have this guy, Giordano Bruno. He was an Italian philosopher, a contemporary of Galileo. And he just basically, his whole job was to say crazy stuff and see what stuck. Here was one of his ideas, and this is a pretty famous quote. "There are countless suns and countless Earths all rotating around their suns in exactly the same way as the 7 planets of our solar system." Remember, this is before we had the 9 and then the 8. And we see only the suns because they are the largest bodies and are luminous. But, and I've highlighted this specifically, but their planets remain invisible to us because they are smaller and non-luminous. The countless worlds in the universe are no less inhabited and no worse than our Earth. Now, the thing is, at this point, 1592, they didn't actually know yet that the stars in the sky were suns just like our sun. He's working on nothing here, and he's just spinning it as far as he can go. But he hits the problem right on the head. Like, he's the first one to really identify the problem is stars are really big and bright, and planets are really small and not bright, which makes them really hard to find. Unfortunately, he had a lot of other crazy ideas as well. And eventually, he was arrested by the Roman Inquisition after his boss turned him over, basically. This is the list of things that he was tried for by the Roman Inquisition. He said a lot of things about the Catholic doctrine, which was a bad time to have said them. But one of the things that he was arrested for was claiming the existence of the plurality of worlds. So in the Catholic doctrine, God creates the Earth, singular, and that's it. Well, the heavens, but there's no Earths up there. This is the Earth. So this whole plurality of worlds idea is in direct conflict with this Catholic doctrine, which is interesting when you think about, you know, Al-Razi's point earlier that, you know, if you have this omnipotent, omniscient God, he can make as many Earths as he wants. So yes, Giordano Bruno gets burned at the stake for heresy. And is secondly most known for this kind of baller statement when he got convicted: "Perchance you who pronounce my sentence are in greater fear than I who receive it," which, if you're going to go out, that's a pretty good way. So in 1600, he gets burned at the stake. All right, let's speed up a little bit. So that's 1592. Let's go 130 years into the future. Isaac Newton comes along. We don't have the Roman Inquisition anymore, which is good. And he basically says the same thing. Now we know more about the stars in 1726, and he's like, well, they're just like the sun. The sun's got planets. Why don't they have planets? Now, Isaac Newton himself was very religious, but he kind of went back to the Al-Razi school of thought, and he was like, you know, there's one God who has dominion over all. If there are thousands of planets, he has dominion over all of them. That's cool. He didn't have a problem with it. The rest of this astronomers were like, okay, still kind of an idea that we can't really test. And one of the important tenets of science is that you have something you can test. So they spend the next 200 years trying to find exoplanets. There's a lot of signals that people are like, this is an exoplanet. And everybody else looks at it and is like, no. It's a star, it's a blip, it's noise. Basically, there's a whole bunch of claims of exoplanets that get roundly refuted. Now, the problem is, we only knew one type of solar system, right? It was the one that we had. It has small rocky planets close to the star, like the diagram I showed earlier, and big gaseous planets further out. So that's what they were looking for. And those turned out to be really hard to find. So in 1952, Otto Struve publishes a paper, and he's like, okay, the planets we're looking for are really hard to find. What if we took something the size of Jupiter, and instead of having it in a 12-year orbit, we move it over and park it right next to the star, and it goes around the star every 2 or 3 days. And this wasn't unprecedented because we already knew of stars that orbited each other on a 2 or 3 day time scale. So if you just took out one of the stars and put in a planet, maybe you're starting to talk about something you could detect. Now, there were massive problems with this because you can't just form a planet next to a star. You have to form the planet out here where Jupiter is, somehow convince it to move all the way next to the star, but not all the way into the star. You have to stop it at 2 days out from the star and leave it there. So it was like, yeah, okay, maybe not. Okay, so skip ahead another 40 years. We have Wolfson and Frail. And they finally see an actual exoplanet, which is very exciting. But it's around a pulsar. So a pulsar is a kind of rare type of star that happens at the very end of a big star's life. When big stars go boom, they supernova, they leave behind something which is a neutron star. And particular types of neutron stars put out these pulses, and those are called pulsars. So they're kind of rare. And any kind of planet that's going around this star is not the same kind of planet that we have. It's either been formed by the remnants of the exploding star, or a nearby star that just got basically blown to bits and left a planet behind. Or maybe it's a planet that got captured after the big kablooey. So basically, this was kind of cute, but it didn't really fit in with all of the rest of our ideas about planets. So it was exciting, but we were waiting for more. And then we got it. In 1995, finally, technology, what really happens is technology catches up with ideas, right? So people build better telescopes, they build better CCDs, better instruments. Finally, in 1995, Michel Mayor and Didier Queloz find one of these short period giant planets that everybody was like, that's crazy, they'll never get there. And they're like, oh, look, there's one. So it turns out these kinds of planets, which we call hot Jupiters because it's a Jupiter that we parked right next to the star, were the first kind of planets to be found around normal stars, stars like the Sun, stars that are just boring middle-aged stars. And I'll show you why they're the easiest to detect, but they were extremely surprising. Okay, so that is racing through 2,500 years of history to the first actual discovery of an actual planet around an actual star. So now I'm going to show you how rapidly the field has been changing in the last 25 years. This movie was made by my colleague Marcy Harbert, and the music is provided by Jeff Laity. Oh, let's try that again. All right, I'm going to pause it right here so I can tell you what I'm plotting. What this is on this axis here, so this is the orbit of the planet. So the Earth takes 365 days to go around the star, to go around our star. This is a log plot, but basically 300 is between 100 and 1,000. So this is Earth here. And this is the mass of the planet in Jupiter masses. So Earth is about a 300th the mass of Jupiter. So Earth would be basically here on this plot. And you're like, wait, Jessie, you just told me that planets weren't discovered until 1992. This is an interesting, just a tiny aside that I'll talk about confidence in publishing your results. This was a group, a Canadian group, who actually found a planet, but they didn't really have the guts to kind of stand behind it. And they were like, oh, maybe this could be one of those hot Jupiter things. And so in retrospect, we went back and looked at it, and sure enough, it's one of those hot Jupiter things, so it gets credit. But it wasn't until 1995 when Michel Mayor and Didier Claude like planted their flag, and they were like, we did it! Capital letters, exclamation mark. So you got to have confidence. You got to go hard. All right, I'll keep playing, and then you'll start to see this diagram got populated. So you can see all of these hot Jupiter things that get found. You can see it starting to push down towards Earth. Oh, but we don't quite get there. Oh, I'll just put it back on that. All right. Sorry, I stopped the dramatic music. So this is one of the representations of the planets that we found today. So what you can see is there's this big population of things that are the mass of Jupiter in just a few day orbits. So these are these hot Jupiters that Otto Struve predicted. You see lots of Jupiter-sized things on Jupiter-like orbits out here at thousands of days. You see small things on short orbits. So these are like Earth-sized things going around their star every 10 days. What you don't see is things down in this corner, things like the Earth. And that's not because they're not out there. It's because they're the hardest to find. So if you think about it, the smaller a planet is relative to the size of the star, the smaller the signal from the planet is going to be. And there's a bunch of different ways we look for planet signals, but basically it's almost always the case that if your planet is smaller, it's harder to see. So that's why it gets harder to go in this direction. The reason it gets harder to go in this direction is because most of these techniques rely on watching the planet go around the star multiple times. And if it's a very long period, then you have to wait a very long time to see it go around and make sure that that's the planet that you found. So this is actually just a bias, we call it. It's not that it's not that they're not there. It's just that at the moment, with our current technology, they're too hard to find. But you saw when this plot was filling out, basically we keep pushing down and down with bigger telescopes and better technology. And the hope is that we get there very soon. So where are we at right now? This is today. I took the screenshot today, August 12th. This is the NASA Exoplanet Archive, which is how NASA keeps track of all of the planets that we found, and this is where I work. So as of today, there are 3,372 planets that we've confirmed around other stars. 570 stars have been found to have multiple planets around them, which is super cool because we know our system is a multiple planet system. And for a long time, with this whole technology thing, we were only finding systems that had one planet, so it was a bit like, wait, are there systems with more than one? Yes, there's at least 570. And we've gotten to the point where instead of it taking years or decades or centuries between discoveries, these are coming out literally every day. This was a new planet that got announced that we put on the archive today. A week ago, there were 3 new planets. This is kind of a lull, actually, because everyone's on summer holiday. But the point is that this number is going up every week. So it's a really, really exciting time to be in exoplanets. So it's impossible to talk about the history of exoplanets without talking about Kepler. So there have been many instruments and people and ideas that have revolutionized this field. But Kepler is really one that stands above. So Kepler is a spacecraft that got launched in 2009. It was 20 years in the making, but it took 20 years for the technology to get good enough to do this. It's a 1-meter telescope that we launched into space. The main goal of the Kepler telescope is to measure how common planets like the Earth are. This is this whole plurality of worlds, cosmic pluralism. Are Earths rare, or are they very common? Are they just littered through the galaxy? And so the point of Kepler was to measure this. The way Kepler works is using the transit method, which I'm going to talk about a little bit more. And what it did was monitor 200,000 stars for 4 years, almost continuously. It just stared at this patch of sky for 4 years. So the patch of sky is shown here. This is the constellation Cygnus, and this is the constellation Lyra. So this is the summer triangle, which if you go out and look at the meteor shower, which I did last night, you'll be looking straight up at the summer triangle. So you'll see there's several thousand planets in this tiny patch of sky. So how does it work? How does the transit method work? So does anybody know what this is? It's Mercury. Venus is an excellent guess, but it's Mercury. So this is a transit of Mercury, and seen from Earth, what happens is Mercury goes between us and the sun. Now, if you were measuring the brightness of the sun, if you were far away, if you were an alien civilization very, very far away, and all you could measure was the brightness, what you'd see is a dip every 83 days, because Mercury would go around, and every 83 days would come and block some of the light. Now, Mercury only blocks 0.002% of the light, so that's very hard to see. Earth is a little bigger, but still not very big. Earth blocks 100 parts per million of the light, so 0.01%. And you can see this is a sunspot, so this is activity on the surface of the sun. The sunspot's bigger than Earth. So if you're trying to measure the brightness of the star and it's got giant sunspots on it that are also, moving and rotating, it's tricky to see things like the Earth. But luckily, we have things like Jupiter. Yeah! Jupiter blocks 1% of the light. Now we're talking. And this is one of the reasons why Jupiters were the first planets we found, because they block a big section of light. And that's really sweet. There are pros and cons to this method. One of the pros is what this method gives you is the size of the planet. All you can see is how big it is. You don't know how much it weighs. It could be a really, really dense ball of iron or a really, really puffy ball of gas. All you know is how big it is. But we do have other ways of measuring the mass. So if you have a transiting planet and you can measure its mass, suddenly you know the density. You know whether it's a puffy ball or an iron ball. And that's really exciting, because that's one of the things we want to know. What kinds of planets are out there? Are they like Earth or are they like Jupiter? We also get access to the atmospheric properties. Now this is cool. So imagine Earth has this layer of atmosphere around it with clouds and stuff. So when the Earth goes in front of the starlight comes through the upper atmosphere of the Earth. Not all the starlight gets absorbed, some of it goes through, because the upper atmospheres are transparent, they let the light through. But there's molecules in the atmosphere that block some of the light, just the light that hits them at the right time, at the right wavelength. So if you took a spectrum of the star without the planet there, and then waited until the planet was there and took another spectrum of the star, the difference would be the atmosphere of the planet. This is one of the few techniques where we can actually measure what's in the atmospheres of these planets. We can start to do things like look for biomarkers. Is there oxygen? Is there methane? Is there some kind of biogenic activity happening? This gives us access to that. But there are problems as well. So not all planets transit. The thing is, you need to be lined up just right. So the only reason we see Mercury transit is because Mercury goes between us and the star. If Mercury was doing this, and we were here, it would never go between us and the star. So most planets don't transit. And that's why surveys like Kepler have to look at hundreds of thousands of stars, because most of them won't transit, but some of them will. So you need to look at many, many stars in order to see this. It just means the missions are more expensive, because most of the time you're looking at something that's not going to transit. And there are also false positives. So these are things that look like they might be transiting planets, but then it turns out they're not. It's like 2 stars or 3 stars or something going on. Activity, like I said, the sunspots. There are things that make you think there's a planet, and then there's not. Which basically, this is my entire thesis, my PhD thesis, in two words. But it's okay, because then I started working on Kepler, which was very successful. It's okay. So this is the impact of the Kepler mission on the exoplanet field. What I'm plotting here is the year, and here is how many planets were discovered that year and how they were discovered. These are the different methods. So you can see the first 10 years or so, or 15 years, is dominated by radial velocity, which is the method that gives you the mass, but not the size. In 2006, a different space telescope called Corot, which was a French mission, was launched, and you start to see this green rectangle, which is the transiting planets, really start to expand. In 2009 is when Kepler is launched, and suddenly in 2010, there's more transits than there are radial velocity. And from there, it just takes off. So in 2014 and 2016, you can see these huge spikes. These are 2 large catalogs of planets that Kepler released. It's finding them in the thousands. So there was 1,200 planets that were released in a paper recently. So Kepler has just really revolutionized, what we know about planets and the sorts of systems that they're in. Okay, so how are we going with our search for Earth's twin using Kepler? So this is the Earth and this is the Sun, not to scale. The planets are all to scale and the stars are all to scale, but the planets and stars are not to scale with each other. Anyway, so we found something the size of the Earth that was too hot straight away. So remember I said the things that are closer are easy to see. They're almost always way too hot. Some of them are thousands of degrees because they're right next to the star. Then we found something which was the right temperature, but it was way too big. So this was something kind of Neptune size, so a big ice giant, which is not what we're looking for. We want something like Earth. Then we found something which was the right size and the right temperature, but around a different kind of star. So this one, Kepler 186, orbits an M dwarf, which is a very, very small, dim, dull red star compared to our medium-sized bright yellow star. So there are lots of questions about how life could arise on a planet around a very different kind of star. So that's cool, but still not exactly Earth's twin. So then we get to Kepler 452, which was a year ago. Now it's the right temperature around the right kind of star, but it's just a little big. This one we think has about a 50-50 chance of being rocky. So it's a 50-50 chance of being Earth's twin. What we call it is Earth's bigger, older cousin. Not quite Earth's twin. So we're not there yet. We're still looking. But in terms of measuring how common Earths are, what we think is that planets like the Earth, in terms of size, between 50 and 200 days. So remember, Earth is out at 365 days, but that still looks like it's too hard. We're not there yet. But 50 to 200 days, we think that 33% of stars, so 1 out of 3 stars, like the Sun, has a planet like this. And that's really exciting, because 1 out of 3, that's pretty common. There's, 200 billion stars in the Milky Way, so that means there's hundreds of billions of planets. So that makes me relaxed, because my job is to find exoplanets, and if they're everywhere, that's a very good feeling. They are hard to find, though. Hence why I keep getting paid. So we didn't find Earth's twin yet, but we found a whole bunch of other stuff, which has been really cool. And this next few slides is just going to be a rogues gallery of ridiculous headlines. Death Star vaporizes its own planet. So this is a disintegrating planet that we found, which is so close to its star and so small that the star's just blasting it away. It's not big enough to hold on to its own atmosphere and surface, and it's so hot that the surface is just melted and getting blasted away by the star. So that's no bueno. No good. So Kepler 16, which is the 16th planet found by Kepler, I apologize very strongly on behalf of all astronomers. Exoplanets have stupid names. Kepler 16b was the first planet found that had 2 stars. So there's a planet and it's orbiting 2 stars. Now, of course, all of the headlines were like, Tatooine, we found Tatooine. This is Luke Skywalker's home planet. The entire of the internet the next day was just Tatooine. But recently we had, move over, Tatooine. Planet discovered orbiting 3 suns. And this is a configuration we'd never really even thought about, because, who knows what's stable or not, but definitely not something we really thought about. This one, blue planet may rain liquid glass. So this is HD 189733, which is one of the first hot Jupiters found and one of the really well-studied ones because it's really bright and nearby. And we can get good measurements. And what they found when they looked in the atmosphere, so like I said, you can atmosphere the atmospheric properties. What they found was that there was evidence of silicates in the atmosphere, but the atmosphere was so hot, it must be liquid, or gas, but liquid could be raining out. So of course the headline, blue planet may rain liquid glass. So don't vacation there. But I just wanted to say to the organizers of the Olympics in Rio, this is the color a swimming pool should be, not green. Okay. 2 baby alien worlds show us how to cook a planet. So recently, and Slate is very good for headlines, I want to say. Recently, we found 2 baby planets. So these are planets that were only 2 to 5 to maybe 10 million years old. Now, of course, that sounds positively ancient, but think about the fact that the Earth is 5 billion years old. And the fact that we don't know how long it takes to make a planet. Some theories are that it takes 10 million years to make a planet. So if you find one that's 2 million years old, well, that theorist needs to look for another job. So one of the things we're really pushing for is younger and younger planets. We really want to pinpoint when do planets start, how long does it take them to form, because that will also give us information of how they form, because different theories take different amounts of time. Orphan planets. It's a hard knock life. So these are rogue planets, or free-floating planets, they're called. So we found these planets that are just out there in interstellar space. They don't seem to be associated with any star. We don't know really where they came from. We have ideas, like maybe they started in a solar system like our solar system and got kicked out. Maybe they formed from a cloud that was just too small to make a star, but there was enough to make a planet, so why not go for it? But recent studies seem to indicate that there are as many of these free-floating planets in the galaxy as there are stars, which is literally hundreds of billions, just out there. And the thing is, they're really hard to find because they're dark. They're not self-luminous. They're planets. But the point is, Bruno was right. There are as many planets out there as there are stars, which is incredibly exciting. So what's next? I'm sorry, I'm speeding up a little bit because I know you want to get out and see the meteors. So this is NASA's roadmap for how we look for planets. These are Hubble and Spitzer are two of the great observatories that were launched previously that have been looking at exoplanets since they've been found. Kepler is the one I just talked about. TESS and JWST are upcoming missions. WFIRST is one past that in the next decade. The opacity of the spacecraft here is whether or not there's funding. So the ones that you can't see through are actually going to happen. And these ones are kind of like fantasies in Charlie Bolden's eyes. So I'm going to talk about two of them, though. So the TESS mission is the successor to Kepler. If you haven't heard, Kepler actually broke. Unfortunately, it can't keep doing the mission that it was doing. But next year, we're launching the TESS mission, which is the Transiting Exoplanet Survey Satellite. It is 4 10-centimeter telescopes, so here they are, 1, 2, 3, 4. And it's designed not to find how common planets are like Kepler. It's not a statistical mission, but it's actually designed to find the nearest planets, the nearest, brightest, best opportunities for follow-up so that we can really study them really closely. Most of the planets that Kepler found turn out to be really far away. So, that's cool, we found them, but you can't do much with them once you find them. So TESS is designed to find the planets that we'll study for the next century. It also uses the transit method, which now you're very familiar with. And it's also monitoring 200,000 stars, but in a very different way to Kepler. So Kepler, this is the Kepler field of view that I showed before. Kepler looked at one small patch of sky for 4 years. TESS is doing the whole sky. TESS is basically Kepler on steroids. So basically everything that's colored is going to be observed by TESS with different amounts of time. Right up at the pole, we're going to get almost a year-long observation. So what this means is TESS is not going to find planets like the Earth, because Earth takes 365 days to go around, and the longest it's going to look in one patch is 350 days. But it is going to find all of these really wacky, interesting, crazy, out there, short period things, which are really fun to study, because we don't know how they work. WFIRST is a mission that comes after that, in 2024. It's a 2.4-meter infrared telescope. Now, remember how I said most things, it's easy to find the hot planets. With one particular technique, microlensing, it's easier to find the colder planets. So microlensing, I'm not going to go into. I don't even understand. There's curves, there's numbers. It's complicated. It's gravity. But the point is that Kepler was sensitive to these short period planets. Just think of this like period. Kepler was sensitive to these short period planets, and WFIRST is going to be sensitive to the really long period planets. And it's out here that we think most of the planets form and then somehow end up in here. We still haven't worked out how that happens yet. Lots of theories going around. So WFIRST is going to complete this census of different types of planets that Kepler started. And it's going to do that by staring straight into the middle of the galaxy for 500 days. OK. What are we going to find? So I like to think that 400 years ago, when Bruno predicted that planets were everywhere, that he'd have no idea what we would find. That what we saw today was completely different from what he even envisioned. And what we've seen is this incredible diversity of numbers of planets, types of planets, configurations of systems, multiple stars, multiple planets. Everything we find is new and interesting and exciting at this point. So the next 10 years, the next 20 years are just going to be this incredible time in the field. And I hope in 10 years' time, after the launch of WFIRST, I can come back here and tell you, we found these other crazy things. Because that's what exoplanets feels like right now. It's really exciting. And thank you for listening to me talk about them.
So does anyone, we have time to take a couple questions about the
Sorry, I took up the time. So it's definitely possible. It's extremely unlikely. The question was, is it possible for a rogue planet to crash into the solar system in either the sun or the Earth? And it's certainly possible. It's very, very unlikely, just because space is really incredibly huge. So the chances that we'd actually collide with anything are pretty small. So I'm not worried about that. I'm worried about my spacecraft failing. I'm not worried about that. Excellent question, though. The media really hyped up the rogue planet part of it. Rogue. Up the back? Yeah.
So, what method or technique do you use to detect the rogue planets if they're not rogue?
So there are two different methods that we've used to find them. One is just directly imaging. So when I said that they are not self-luminous, a lot of them are still kind of warm, just because they're still contracting. And so if you use an infrared telescope, which is kind of like night vision, if you look at the sky with night vision, sometimes you see this tiny little, very faint blob. And you can work out from models that that must be a planet-sized blob. And the other way is microlensing, which is where the planet goes in front of a background star, and gravity bends the light of the background star such that the background star suddenly looks brighter and then fainter again. So you don't actually ever see the planet. What you see is the background star get magnified by something going in front and bending the light. So you can, if you have a planet, it gives you a very characteristic curve. Down the front?
Would it be possible if, like, a solar system like ours would be able to, like, rotate around like a giant sun, like a giant sun?
So the question is, can we have solar systems around giant stars? And the answer is yes. We've actually found planets around stars much, much bigger than the Earth. They're hard to find planets around because they're so big compared to the star, and it's the size of the planet compared to the size of the star that tells you how hard it is. But they have been found, mostly of the Jupiter-sized things, because Jupiter's big enough. But that was another thing that we weren't really sure whether we would see them, and then there they were.
Do you know how long it will take to terraform Mars if we actually get there?
Oh, so we need a JPL person to come and talk to you about that. I have no idea, I'm sorry. JPL person in the audience, anyone? All right, I'm sorry.
You mentioned your area was determining false positives. Is there a probability, or what are we talking about? How do you do that? I mean, if you're going to verify the reaction.
Right. So one of the ways, so the question is, how do you find false positives? One of the ways is you use the other technique, which gives you the mass. So you look at the radial velocity and you measure the mass. And if it's a stellar-sized object that's making the transit, then you know it's a star. It's not a planet. So one method gives you the size, and the other method gives you the mass. And you can be fooled about the size of the thing you're measuring if there's really two stars and you didn't realize. Another way is you can look for sunspots. So you look for the activity of the star, and there's various ways you can measure the activity. And if the measurement of the activity is the same as the period of the planet, then you know that it's being caused by stellar activity. So for instance, our sun has this 11-year magnetic cycle, the solar cycle. So if you were far away watching the sun, you would see some 11-year solar cycle thing. And you would have to make sure that you understood that that was the star, not a planet on an 11-year orbit. How big are the star spots? That's a really good question. So the star spot that I showed was about 2 times the size of the Earth, so 14,000 kilometers. But that's just on our sun. We have lots of different types of stars, and some of them have different sized sunspots. But they're very, very big. Huge, bigger than Earth. We wouldn't want to be right there. Up the back? Yes? If one of the rogue planets went into the sun?
No.
Sorry, I didn't quite hear it. Can you repeat it? Oh, yes, yes. Okay, so the question is, if a rogue planet got captured by the sun, would it be a planet? And the answer is yes, and probably some of the planets that we've found are captured planets, which is exciting, because, you know, if there's as many rogue planets out there as there are stars, then some of them have been captured. Good question.
You mentioned that there's an exoplanet that had where it rains liquid glass. Are there any other exoplanets that
Well, there's one that rains liquid iron, but, you know, that would be boring to have 2 things on my presentation that rain liquid things. There's one planet that's pink, just because of the color of what it's radiating and its atmosphere. If you saw it with your naked eye, it would look pink, which is kind of cool. There's one planet that's egg-shaped, it's so close to the star that the gravity of the star is actually stretching the planet out. So instead of the planet being a sphere, most of the planets in our solar system aren't perfect spheres. They're a little bit elongated. So this is like dramatically like egg-shaped. So those are just some of the other crazy things. I couldn't fit them all in. I had to let you go at some point. Really good question. What makes the planets their colors? So a lot of it has to do with what's on the surface of the planet or on the surface of the atmosphere. So for instance, Earth is blue because most of the planet's covered in water. But Neptune is blue because the atmosphere is full of methane, and methane just happens to emit or absorb? No, I'm going to get it wrong. It's because there's methane. So Jupiter is brown because of the various things in its atmosphere. It's got to do with what's on the surface of whatever it is.
All right. Okay, I think, can you all hear me? Yes.
Yes.
All right, so let's give another round of applause for our excellent speaker. All right, and if you guys are not paying attention, please be a little quieter so that the people who are paying attention can hear what I'm saying. So this is just going to be like 5 minutes long about the meteor shower, which is going on now, and maybe you've heard about it in the news. So first, I want to explain about where this meteor shower comes from at all. So all meteor showers are actually originate in comets. There's a comet which was called Swift-Tuttle that was discovered in the 1800s. It takes 133 years to complete one orbit around the sun. So this red line is the orbit of the comet. Jupiter's orbit is right here. It's kind of hard to see. Saturn is here. Pluto, not a planet, is out here. And all of the inner planets are in this tiny little area here. So this has a super giant orbit. It's actually not that different from other more famous comets, like Halley's Comet, which for some reason I blanked on. So basically the comet travels through the inner solar system and it leaves behind a trail of debris. So this is a picture from the last time that the comet came by, which was in 1992. And this is a series of pictures taken over several days. And of course, you know what comets look like. They have like a big nucleus of kind of a snowy ball, and then there's a huge tail afterwards. And so the tail is what causes meteor showers. Basically, if the Earth passes through the tail, because the tail is still kind of orbiting around the sun and it's out in space, if the Earth passes through the tail, the little bits of dust and stuff from the comet will enter the Earth's atmosphere, and then mostly they burn up on their entry into the atmosphere, and that's what you see as the meteor. So for this particular meteor shower, it's called the Perseid Meteor Shower because it looks like it comes out of the constellation Perseus. And I don't know if can you guys recognize Cassiopeia in the sky? It looks like a giant W. It's sort of on the other side from the Big Dipper. But if you look right below Cassiopeia later tonight, you'll be able to see that's where the meteors will appear to be coming out of. And this meteor shower is very exciting in particular because it has a super high, what's called a zenith hourly rate, ZHR, which is what this plot is showing. It's basically the number of meteors per hour that you can expect to see. And this is the date. And so you can see there's this huge spike, which actually happened last night, where you were getting over 200 meteors per hour. So if there's 60 minutes in an hour, you're getting like 3 meteors per minute, which is a lot. And then there's a little bump here, which is earlier today, if it was dark where you were. But there's still plenty of meteors that you'll be able to see tonight, more than 1 per minute. But really, if this lecture had happened yesterday, it would have been better. So the best way to see them is actually not from here, unfortunately, because there's a lot of light pollution. So this is a figure that just shows what you can see depending on where you are in terms of the night sky. So this is the inner city sky, which is like if you went to downtown LA. And then I would characterize Pasadena as urban-suburban transition. So you can see some stars, but it's not super awesome compared to some place like the dark sky site. So if you're really into seeing the meteor shower in its full glory, you can drive up into the San Gabriel Mountains. It's only an hour to get up into the middle. And you'll be able to see a lot more meteors than if you just stick down here at Caltech. Or better yet, if you don't have anything to do the rest of tonight and also tomorrow, you can go to Death Valley, Or you can go to Joshua Tree, where the night sky will be fantastic and beautiful. And even if you don't do it right this moment and run out to your car, I do highly recommend at some future point that you go to a dark sky site, because it is very awe-inspiring. And also, there's tons of other meteor showers, so even if you don't go to Death Valley for this one, you can go to Death Valley for a different one. So think about it. The other thing is that so the meteors are much easier to see after the moon sets, so later on in the evening. So looking towards the northeast at like 11 p.m. or even later after midnight, you'll be able to see the constellation of Perseus, and then the meteor showers appear to be coming out of it in this, as shown in this diagram. So this, again, is Cassiopeia, the W. And if you go outside to look through the telescopes, you should definitely ask the volunteers, who are all wearing things that look like this. Ask them where Cassiopeia is, and they can point it out to you, and then you can remember it for later to take a look. If you still want to just try looking for meteors, because why not, I suggest that you first look through all the telescopes, and then lay down in the field facing northeast, which is like that way, and look up at the sky, and try not to look, yeah, towards Mount Wilson. Try not to look at any lights or anything, and just look at the sky and enjoy the view, and ideally don't lay down in a puddle or something. I don't know what the quality of the field is, so that's at your own risk, but just wait and be patient and think about the beauty of the stars, and then you might be able to see some meteors. And this is just, this is a time-lapse picture from the Perseids in 2009. And this, I thought, was a really nice example of how the meteors appear to be coming from a particular location. That's why it's called the Perseid Meteor Shower, because Perseus is here, and they're all coming out. But this meteor shower is really spectacular, but there's actually 12 named meteor showers, so basically one per month every year. So just because you don't see it now doesn't mean you can't. And if you're in a dark sky site, like even any day of the year, you can see meteors. They just happen. So it's a reminder of how spectacular the universe is that you can see every day if you're lucky. All right, so that's the end of my presentation. Congratulations for you for staying. And if you have questions about meteors, I can take a couple questions about meteors, and we'll get set up for the Q&A, which will happen. And if you want to go outside and actually see the sky instead of just talking about it, then feel free to do so. Yeah. What? It's leftover bits of comets that fall into the Earth's atmosphere. So it's like just tiny, like really teeny tiny pieces of dust, basically, or like little rocks. Yep. So the question is, why do meteors seem like they're coming from one specific spot? And the reason is because the meteors are all in, the little bits of dust and rock are all arranged in a line, and as the Earth like basically plows into that line, they're all coming from the same area. But once they enter the atmosphere, and depending on where you are, the exact trajectory or the apparent trajectory, like the path that the shooting star takes, isn't always the same. So it's not like they start at the same place and always end at the same place. They're sort of random, but they all enter the atmosphere in the same place. So that's why they all seem like they're coming from the same section of the sky. All right, so why don't our panelists come and sit down? You're free to go whenever you want, unless you want to be on the panel. All right, so I'm just going to have each of our panelists introduce themselves, and in case you forgot me from earlier, my name is Erica. This is me. I am a postdoc here at Caltech. I have been a postdoc for 2 years. My specialty is building telescopes and cameras and instruments, mostly to study galaxies, but maybe for other things too. And now Ron will introduce himself.
Hello, my name's Ron. It's spelled like that right up there. I work on, well, I'm a grad student here, entering my second year. So my area I work in is black holes, gravity, gravitational waves, and all that cool stuff.
I'm Mike Wong, and I'm a grad student in planetary science. I mainly study atmospheric chemistry of planets in the solar system, but feel free to ask me anything related to planets, and I'll try to help.
I'm kind of the odd one out. My name's Elise. I'm an undergrad, actually, in planetary science, and I can answer some questions on astrobiology if you guys are interested in life in the universe. So could Mike.
Okay, does anyone have any questions? Yeah.
I guess this is for Elsie. I noticed on your shirt you have Europa. Is the understanding that there might be water below the ice? Because there was, is there a probe that's on its way to do that?
Okay, so
help us out with that.
The scientific consensus is that there's pretty much water inside of Europa. An ocean about 100 kilometers deep, or a water and ice layer about 100 kilometers deep. And the work I'm doing at JPL this summer is actually trying to figure out what that ocean is like and whether or not it could be hospitable or whether or not life could have emerged there, whether or not it's there today.
Would it be warm from the core, or how would it be warm enough so that it on the surface?
So there are a number of ways. So there wouldn't be a surface that you could land on and then like go swimming in. It would be covered in an ice shell. Europa has a really tenuous atmosphere that's mostly, it's pretty much vacuum, but there's a little bit of oxygen. But there's an ice shell over the ocean. And if the ocean exists, there are a couple of ways it could stay warm. Some of the heat is primordial, from when Europa formed. So it's just leftover heat. And then there are long-lived radioisotopes that decay and give off heat, so that's part of why the Earth is still warm too. And then Europa, if you imagine it like a blob of Play-Doh, as it goes around Jupiter, Jupiter's gravity kind of squeezes it. And it's called tidal heating. And so some people have done some really fancy calculations I don't understand about that, and have convinced quite a number of people that there could have at least been one period of time where Europa was pretty warm because of that tidal heating.
Okay, I think we have another question.
For Ron, how are black holes made, and like what are they?
It's a question we all want to ask. So black holes, how they're made. Essentially, you have this whole process of how they're born. When stars die, especially like supermassive stars, very big stars, they essentially explode. But the center of it collapses to a very dense object. And we're pretty certain that's, like black holes form from that, because black holes are essentially really dense objects, really dense stars that, stars are supported. There's like a battle between forces. There's like different types of forces, like nuclear forces and like the E&M forces that sort of keep the star from like falling in on itself, because you have gravity pulling it down. So when this other forces sort of like lose this battle and gravity dominates, it'll form like a black hole. That's essentially how they're made. What was your second question? What are they? Matter, really. Matter, it's kind of weird. So essentially just they're formed by matter collapsing, and they're holes in space-time. But you can't, it's not like typical matter. You can't go and take a chunk of a black hole like you can do with a star. So you can go out there, like, theoretically you could take a teaspoon of a star and like say, oh, it weighs as much of an elephant or something. But with a black hole, you can't really do that, because they're like literally holes in what we call space and time. Yeah.
So what happens when something falls in the hole?
They go through a wild ride and eventually ripped apart. Well, so if the black hole is like not big enough, you get these what they call tidal forces, the same type of force that gives tides on Earth, essentially. Gravity can be pulling in different directions, based on how big an object is. Mm-hmm. So if the black hole is like pretty small, you have all these tidal forces being experienced from your head and your foot. They experience different forces that'll like rip your body apart, basically. But if the black hole is big enough, you could fall right through. There's no tidal forces that'll rip your body apart. But just the person who falls in would experience what it feels like to go through what they call the event horizon.
Yeah.
Because so like outside observers, someone far away, they won't be able to like see that process of you going through the black hole. Essentially, you fall onto the surface of the black hole, the event horizon, and the image of what you were gets frozen on the surface of the star. But since gravity, sort of like causes this redshifting effect, basically stretches light waves very rapidly. Gravity's so strong that it actually also stretches the light waves that are coming out. So it changes like the frequency of the light being emitted. So your light gets redshifted, what they call redshifted infinitely, where it falls outside our visible spectrum. So essentially, that's why the black hole is black.
So you say if the light falls in, it gets
Redshifted, yeah. So essentially, the E and M waves, they get stretched infinitely long, yeah.
What do you think is beyond the event horizon?
I don't know. Yeah.
Related to this, actually. Can I ask it?
Yeah.
Cool. All right, so you're talking about redshift. And so one of the properties of light is that the energy of a photon is manifests as the frequency of its wavelength. So when you have a photon getting redshifted, meaning its frequency goes down, its wavelength expands, it's losing energy, where does all that energy go?
You know the answer to that, Leo?
Energy doesn't have to be conserved in general relativity. It doesn't. I didn't know that. Okay.
Energy doesn't have to be
Conserved. Okay.
so you can.
Exactly. Right. Okay. Cool. Moving on.
Is the reverse possible?
Well, my statement was a little glib, maybe. It was too simplistic. Energy, the law for conservation of energy is different in general relativity than it is in, Newtonian physics. There's still a conservation law at every point, but you can't compare energy here and energy over there. So, and also different observers that are moving at different speeds relative to each other will measure different energies. So when energies change, it's just like, well, that's, that wasn't a quantity that made sense to begin with. So, no big deal. Okay.
There's a couple questions.
I think we had a question over there.
At the last astronomy on tap, somebody mentioned, one of the people I gave one of the first lectures there, they mentioned that pretty much any molecule you can think of, it's somewhere out there. And they were arguing that ether is out there too. But anyway, but then I remember also, I don't know if people still anybody believes in this theory or anybody thinks about it still, but somebody said that maybe life came from out there because maybe the beginning molecules of life just came to Earth from outer space, and that's how life started on Earth. So does anybody still believe that too?
All right, I think we know who to hand that to.
So you asked if whether or not life on Earth could have been seeded from elsewhere. So yes, the short answer is yes, it could have happened. There are people who are actually really concerned that if we find anything on Mars, we won't be able to tell if it was life that started there or if it was ejecta, a microbe hitched a ride on something, big rock from space hits Earth, something gets ejected, lands on Mars. Very low probability, but it could happen over the insane periods of time that we think about. And some people have done some work to show that it's possible for life to live inside of, simple life forms to live inside of rocks in space. So it's certainly possible. It's probably unlikely. That's probably an answer you'll be hearing a lot when it comes to these kinds of questions, because we can't say it didn't happen, but it is something that people think about happening on Mars, so who's to say that life didn't emerge somewhere else in the universe or in our solar system, and then wherever it was got hit, and hitchhikers from that world ended up here. I can't say it didn't happen. Personally, I don't think that's what happened, but it could have happened.
All right. How about, you haven't asked a question yet, right? Yeah.
How do black holes end?
The question is how do black holes end, or what happens to them, I guess. Yeah, so there's a current way of thinking about it right now is saying that black holes eventually evaporate. So the whole universe is going through this whole constant expansion. Disorder is always increasing, and so essentially at the end of towards the end of the universe, only thing left would be black holes. But black holes, after they, either they suck everything in there and everything like that, they'll be radiating this energy, what they call Hawking radiation, and so that also changes the size of the black hole. So this process actually makes the black holes evaporate over time. So at the end of the universe, even black holes will evaporate and not exist. So yeah. Yeah.
You have another question? Okay.
So are most planets made out of, do they have the same material as the inside of the Earth, in their inside?
So the question is, do most planets have the same material inside of them as the inside of the Earth? And so first, let's just review what the inside of the Earth is made out of. Right under our feet, we've got lots of rock, silicates, and then beneath that, we have a lot of iron. So there's a liquid iron outer core and then a solid iron inner core. And to first order, I would say yes. Small planets about the size of the Earth are made of about the same things. And we know about the planets in our own solar system, and we know about the building blocks of those planets because we have these wonderful things called asteroids. And sometimes an asteroid comes down to Earth, becomes what we call a meteorite, and then, boom! Yeah. But when we find it on the ground, we are basically looking at the building blocks of terrestrial planets like our own. And we can examine what they're made out of, and yeah, they have rock and they have iron, and so we can surmise that Mars and Venus and Mercury are all made of similar things. Now, when you get to the outer solar system, we've got these gas giants. Looks like you have another question. And so the gas giants are basically larger versions of these rocks, but because they're larger, they have the gravitational pull to also contain a lot of atmosphere, and basically you get a lot of atmosphere surrounding those cores.
You have another question? Does anyone else have a question?
I was going to ask about the chemical compositions of the Earth based on life or something like that.
The bioscience?
Yeah.
Like what we'd look for somewhere else?
Or do we have that here on Earth? Or
Oh, yeah, okay. So there was a really famous kind of thought experiment that was actually done by Carl Sagan, where they had a probe that was flying, that we were sending out to Jupiter, and they had it turn and look at the Earth as it went by, and they pretended to be aliens that didn't know, like this actually happened. They pretended to be, they pretended to be aliens looking at the Earth, and they were like, can we say for sure that there's life on it? And so one of the things that gave them a really good idea that life was happening was the amount of oxygen in the atmosphere. It's rather unusual to find a planet that has as much oxygen as we have without there being a lot of life. And when the Earth started, there wasn't this kind of oxygen atmosphere. Life did that. So it'd be unusual to find an oxygen atmosphere. It's not proof there's life. And also plants. They were talking about that spectroscopy or spectrometry that people are doing, looking at the light that comes through atmospheres. So plants have evolved to absorb light very, very well at a very specific range of wavelengths. So if you have your instrument looking at a planet that has these huge forests, like I think we were looking at South America for part of it, and you'll see a very specific dip in the spectra that represents where those plants are absorbing. So that's good evidence for life because it's really unusual to find any kind of geochemical that will do that very specific narrow range absorption that chlorophyll will. But really they weren't able to say for sure there was life until they saw the radio signals.
Animal also?
One thing people think about looking for animals is methane. I mean, this is actually something people want to send. A lot of people in the kind of astrobiology community want there to be something called an atmosphere sniffer on. Yeah.
Technical term.
Yeah. On one of the Mars missions, because then you could, like, I guess if you imagine like the rover going around like a bloodhound, sniffing the dirt, and you could see, wow, there's a lot of methane coming out right here that we can't explain geochemically. And there are quite a few strange metabolisms, like things that we don't do, but that soil bacteria do, where they breathe something like a mineral, and then they put out methane, or they take in methane and put out something else that we can measure. So sniffing for methane is good. Hydrogen is also rather important. There was a study done by somebody who predicted what the amount of hydrogen in Titan's a moon of Saturn, what that atmosphere would look like if there were communities of bacteria or microorganisms that were living at the surface that were using the hydrogen to combust acetylene for their metabolism.
Those microorganisms would...
They would use hydrogen in their like, you know how we use oxygen to breathe? They would basically breathe hydrogen. Yeah. And what that would look like. So there's a lot of thought that's been put into looking at atmospheres to figure out like how life has messed with it and how it would look funny. And basically, life is the last ditch hypothesis. So if you can't explain something using geology or chemistry or physics, you might be like, oh, I have to say that maybe there's life. But nobody wants to stake their career on that. So, yeah.
But out there's a lot of atoms also, right? In the universe.
Yeah. Oh, yeah. Did you have a question?
Yeah, for Michael. Sure. The red spot on Jupiter was in the news. What's that about?
Do you remember the article title?
Something that created heat. Yeah. Something that was generating some form of heat or something, warming up something or creating heat. Yeah. Sorry, I didn't get more.
Yeah, no, that's cool. So yeah, the question was, what's up with Jupiter's red spot? It seems to be creating heat. I haven't read this article, but from what I know about Jupiter's red spot, oh, I can just read you the article. Would you like that? Would you like me to just read you the article here? Is likely a massive heat source. Okay. Right. Okay. Well, first of all, the red spot is basically a giant hurricane. You know, you can think of it like that. It's a giant hurricane, right? And so I'm just going to talk about hurricanes now because I don't really know what the... But okay, so what is a storm, basically? A storm is when you have a lot of hot air that suddenly rises. And that hot air then cools, and the water vapor that is in the air condenses because it's cold, and then it rains out. And so hurricanes, monsoons, and everything like that, they occur along Earth's equator because that's where we get the most sunlight, that's where there's a lot of water, and then the water evaporates, condenses, and rains. Right? So Jupiter's red spot just happens to be a giant hurricane. And so I'm not surprised that it is giving off heat in that fashion. You know, it may be just like a discovery that somebody actually measured this heat, but it doesn't surprise me at all that Jupiter's red spot is actually a hot spot. Oh yeah, it's red.
And I guess this is for Ron. You talk about where there was you defined a black hole, and this was a star collapsing. How about two stars in their reasonable proximity where they might affect each other collapsing? And what is the effect? What would that do? Would there be any different than a single black hole, or would the fact that there's two in reasonable proximity collapsing create something unusual?
Oh yeah, so if you have like, like two compact objects like black holes or stars, you know, close enough to each other, they'll be orbiting each other, which produce the gravitational wave detection that you might have heard about back that was announced back in February. So yeah, so the idea is, well, most of these black holes would like form in like binaries, is sort of like what our understanding is so far. You know, just the whole evolution of two binary stars. You know, where eventually one will become a black hole when it dies, and the other one would collapse maybe down to like a neutron star, also a black hole, through some intricate astrophysical process. But at the end state, if you have something like two neutron stars or two black holes orbiting each other, the idea is that gravity is described as curvature of space and time. So the situation here is that you have any type of accelerating massive object will cause like a rapid deformation in space and time. So if you have like a massive, like black hole or something like that, when they're orbiting each other, they're accelerating around each other all the time. So since they're accelerating, they're causing this rapid, distortion of space-time, which actually takes away energy from the binary system, like the orbital energy and angular momentum, and that essentially drives them to in-spiral closer and closer. And the gravitational waves being emitted, they'll increase as they get closer and closer, so they'll in-spiral more rapidly, and that's essentially what gravitational waves are, and that's what was detected recently. So that's essentially, all types of compact binary objects would end up doing that. Yeah, and then they become one. So if you have two black holes, well, if you have any one of the compact objects is a black hole, you'll get a black hole at the end state. But two neutron stars, if they collide, they can also collapse down to a black hole, because they'll be like maybe like 1.4 times the mass of the sun. So there's a certain like size of a neutron star can be before it would collapse down to a black hole. Essentially, like the forces that are keeping the star like aloft in a way is not strong enough, does not overcome the gravitational pull of this very dense star.
Yes.
I have a question about telescopes. So I guess the talk that we had today, she described some great new space-based telescopes, but are there any cool new ground-based telescopes that people want to build too?
Yeah. So right now the trend is to build the trend is to build really big telescopes. So the current big telescopes are on the order of like 8 meters or 10 meters or kind of around that size. And when people describe the size of the telescope as being like X dimension, that's the diameter of the primary mirror, so like the big giant mirror at the bottom of the telescope. So an 8-meter telescope has this super huge mirror. And you can't actually make a single mirror that big, so it's a segmented mirror made out of many, many parts. And so in order to have to be able to do as much science with a ground-based telescope, you need to have a bigger telescope, and so the trend is to make like 30-meter telescopes. So there's a telescope that's in the planning stages that is going to be built by a consortium of a couple of countries and Caltech and the UC systems. That's called TMT, which stands for the 30-meter telescope, because astronomers don't have creative names for telescopes or anything really. So the 30-meter telescope would have a primary mirror that's 30 meters long, or 30 meters in diameter, and they had picked out a location in Hawaii, and now they're considering other places. And there's a similar project that's for the extremely large telescope, which would be also around 30 meters in diameter. And then there's like a way in the future project of a 100-meter diameter telescope, and I forget, it's like the very extremely large telescope or something, like not very clever. But so for the most part, the trend is to build just a bigger and bigger telescopes. There are other people who focus instead on building small telescopes that can see almost the entire sky, or have very, very large fields of view. And those telescopes are used for, instead of just trying to observe the really faintest, most distant objects, they're trying to find objects which vary with time. And so they're focused on what's called the time domain. So if you can cover a huge part of the sky, and you can take an image every second, then you can monitor all of these stars and see what they're doing. So that's a way, for example, of finding transits, depending on how good your telescope is. But you can also find like supernovae that go off, or all sorts of transient activity throughout the universe. So there's a lot to be done with small telescopes, but also everyone loves a supergiant telescope. Maybe that will be the name of one in the future, the supergiant telescope. Any other questions? Yeah.
Considering the actual technology about telescopes, so how far we can see with all different kind of views we have with certain telescopes?
Okay, so the question is, how far can we see with the current technology? And the answer depends on which wavelength you're observing in. So, for example, if we observe in the microwave part of the spectrum, you can see the surface of what's called the surface of last scattering. So it's like the very farthest, it's not a thing exactly, the farthest distance possible. It's basically like the signature of the Big Bang is visible. And so that is, you're looking back in time like over 13 billion years to what's probably the most distant like phenomenon that can be viewed through a telescope. But then if you're talking about looking at the visible part of the spectrum, we have looked at galaxies that are really, really far away and super old, but they're nowhere near as old as that surface. So, and then with that, it also just depends on how long are you looking. So the deepest view, one of the deepest views of the universe in the visible is the Hubble Ultra Deep Field, where they took the Hubble Space Telescope and just like looked at the same patch of sky over and over for a really long time. But if they looked at it for twice as long, then they would be able to see even farther and deeper in. So it's also a question of like what resources do you have? Any other questions? Yeah.
Do you think you can expect Hawking radiation from black holes?
Do you want to talk more?
No, I'm good. Would we expect Hawking radiation? Can I explain it? I'll try. So I think the idea is sort of, you can think of it as just like a type of argument, I suppose, like quantum effects would generate electrons and positrons all the time in pure vacuum. It's just that, you know, they always annihilate immediately afterwards, so to speak. Because, you know, they exist for a fraction of a second and they'll annihilate with each other very rapidly. And we can maybe probe these similar effects, you know, but with like these, like the Large Hadron Collider and things like that. But for black holes, it's the idea is that there's so much, like the black hole has such a strong gravitational field, is that when one gets created, before they can annihilate, one gets sucked in while the other one comes off of the black hole. So this, like since energy is not being conserved in this type of a scenario, you can sort of make the argument that a particle of a certain type is falling into the black hole while one's being released. So in a sense, you know, it'll decrease the size of the black hole, was the particle being created coming out, like the positron or something. That'll be what Hawking radiation is, essentially. And this is sort of a very like a isolated explanation for a single event, but it'll happen over the entire surface of the black hole. So it's possible like this type of radiation coming off of it. And the black hole would be getting smaller and smaller.
Go ahead.
Do you think you could use that radiation to see more of what's going on inside the black hole?
Possibly. I think the problem is that we just can't observe it yet. It's too dim. The only type of signal we've gotten from black holes are, you know, gravitational waves, which, you know, we detected their in-spiral event. But observing black holes with actual telescopes to see any type of radiation from it is far off into the future. So most of the effects to the electromagnetic counterparts to these type of black holes will be like dominated by like other like astrophysical environments around the black hole. Like you can get these what they call accretion disk. I guess you can think about like stars being ripped apart. Torn apart stars sort of just like orbiting around the black hole. So most of the E&M radiation we hope to detect will come from that observationally.
Any more questions? Yeah.
Well, I found this one right here. This is an article. LIGO-detected black holes may be the origin of dark matter.
So what's your question?
And well, I haven't read the article. I don't know if that's.
Who wrote it?
I haven't heard any more about that. Good theory, bad theory.
I'm sure there is some theory out there. I've not really heard about it yet.
Well, I would say LIGO definitely detected black holes merging. About the other part of that article, I don't know.
Maybe I don't have that also. Maybe you're just thinking that black holes are much
small relative to astrophysical sizes, small enough that they have not radiated away due to Hawking radiation yet. So I think that the calculation that this article was referring to was saying something about whether or not black holes, or whether or not this idea that dark matter was due to primordial black holes was plausible based on, how many black hole binaries have been detected by LIGO so far. But I think the consensus of astrophysicists would say that it's not plausible that dark matter is due to primordial black holes. It's a fine calculation to do, but it's probably not true.
Any other questions? If you guys are also free to come up and, I realize everyone is sitting in like the 5th row and back. If you want to move up. All right. Well, if you think of anything, we'll stick around here for a couple minutes, probably just chatting to each other. And also feel free to go outside and check out the telescopes and be on the lookout for meteors. Yeah.
Just one quick question. You said that if you go up to Mount Wilson, you can probably see the sky nicely.
Yeah.
Do they close the roads to the mountain?
So you can't go to Mount Wilson itself, like there's the little cafe, and then there's the observatory on the top of the mountain. So that gate gets shut, but you can. There's a ton of campsites and even just pullouts all along Highway 2. The map that I showed.
But I thought they closed the roads when you started to get into the mountain.
No, they only close the road if there's a fire or an accident or something. But the blue line on here is actually just Highway 2, and then it keeps going up to the right edge of the map. So you can go along there, and there's a bunch of locations. But basically, as long as you're kind of on the other side of where Mount Wilson is from here, then the mountains will mostly block the light from LA. Yeah. But there are some that, the thing that's on there is a picnic area which closes, but there's also a campsite that's open all night. So, yeah. All right. Thanks for sticking with us.